I want to give a quick disclaimer that this video is intended for college engineering students or anyone who is generally curious about 3D classical mechanics. I do not think it is necessary for high school AP Physics tests. Also, this video is a super high-level overview, and if you want more depth, I recommend reading Professor Paul Midige's textbook on advanced dynamics and motion simulation. Now, if you took physics in high school, you're probably familiar with 1D motion. An example would be like this car that has force going forward, force of drag pushing backwards, gravity going down, and some normal forces pushing up. Now we only care about motion in one dimension. So we'll label the dimension like x, and we have f of x equals m times the acceleration in x. And you can solve for this pretty easily. So you got force of the wheel minus force of drag equals mass times the acceleration of in the x direction. And that's your equation of motion. It's more or less pretty straightforward. But what about 2D cases? There are multiple dimensions at play now, so how do we even represent force and acceleration? Even better, what about 3D cases, like a multi-joint robotic arm? Now, you'll see later that if we can get a general form for 3D cases, we can simplify it down to solve for 2D or 1D cases as well. So what is the general form of F equals ma? To answer that, first we must ask, what is acceleration? Which is not a trivial question. Before we move on, I want to encourage you to watch my previous video on angular velocity and the golden rule of vector differentiation. That knowledge will come in handy for understanding acceleration. In 3D, acceleration is represented as a vector. This vector describes a point, which is important, not an object or a planet or anything else, but a geometric point that accelerates in some reference frame, which we will call n here. So the acceleration of a point in reference frame n is the time derivative in reference frame n of the velocity of that point in reference frame n. And the velocity is the time derivative in reference frame n of the position vector of that point from another point fixed in reference frame n. This is probably super confusing right now, so let's do an example where I walk through calculating the acceleration vector. Let's take an example of a rigid beam attached via a pin joint on the Earth. Let's label a point at the end of the beam as point Q, and the attachment location as point NO. Note that NO is fixed relative to the Earth. Let's also draw rigid bases for reference frame N of the Earth and reference frame B of the beam. Let's also label the length of the beam as L. To get acceleration, first we need a position vector from a fixed point in the desired reference frame to the point that we care about. In this case, the vector is from point NO to point Q. This is equal to L in the bx direction. Let's also define the angular velocity of reference frame B in frame N, which will be useful soon. To calculate velocity, we need to take the time derivative of the position vector in reference frame N. Since the position vector is represented in unit vectors of reference frame B, we can use the golden rule of vector differentiation here. The time derivative of L is 0 since it's a rigid beam, and the next term is the derivative of theta times L in the direction of BZ cross BX. Thus, the velocity of point Q in reference frame N is theta dot LBY. The acceleration of point Q in reference frame N is equal to the time derivative in reference frame N of the velocity vector. Again, we can use the golden rule of vector differentiation here because the velocity vector is represented in B. This gives us the second derivative of theta times LBY plus the angular velocity cross product with the velocity vector. This gives us an acceleration vector of theta double dot L by minus theta dot squared L bx. Now we are ready to look at a general form of F equals ma. This equation is valid for any mechanical system, which includes a particle, a rigid body, a flexible body, a set of particles, and a set of objects. So here's the equation. The left-hand side is the resultant vector of all force vectors acting on the system. The right-hand side contains the total mass of the system and the acceleration of the center of mass of the system in a Newtonian reference frame. There are some important concepts to discuss about this equation. First, F equals ma is an equality. It is not a definition. In other words, the physical phenomenon called force is not defined to be mass times acceleration. Rather, a force is merely equal in magnitude and direction to mass times acceleration. It is a mathematic equality that has been proven to be reasonably accurate on Earth, so in engineering, we deem it good enough for most practical applications. Next, we need to understand this concept of a Newtonian reference frame, which is crucial for ensuring F equals ma is valid. A Newtonian reference frame is a non-rotating, non-accelerating reference frame from which we can base all other reference frames. However, this means that a true Newtonian reference frame does not exist in our universe, because our universe is always expanding with no center of the universe. So as engineers, we approximate Earth as a Newtonian reference frame. This can become inaccurate for large objects, such as other planets, or long time periods, such as hours, days, or more. Now, you may be thinking, wait, this definition of a Newtonian reference frame is inherently flawed if it only works on Earth. And yep, you're correct. F equals ma is a flawed model, but it is useful for engineering purposes. Which brings us to this famous quote that all models are wrong, but some are useful. If you want to learn a more accurate model for motion in the universe, you can check out Einstein's theory of general relativity. But as earthbound engineers, we're happy enough with F equals ma. Let's take a look at F equals ma in the context of our spinning beam example. First, I'll clean up this drawing to add some forces. Let's say gravity and a force applied at point Q. I will also write the angular velocity vector here for reference. Now let's write out F equals ma. First, we can write an expression for the force vector, which is negative mgny plus faby. Let's move that aside and get an expression for acceleration. We first need a position vector to the center of mass from a fixed point in a Newtonian reference frame. In this case, that would just be half the beam length in the bx direction. We can use the golden rule of vector differentiation to derive velocity, which becomes the derivative of theta times L over 2 by. We can similarly derive acceleration using the golden rule, and we get an acceleration vector of theta double dot L over 2 by minus theta dot squared L over 2 bx. Now, we can write out our F equals ma equality. We write the force vector on the left side, and mass times the acceleration vector on the right side. We want to convert this vector equation into scalar equations so we can solve for the relationship between forces, such as Fa, and motion parameters, such as theta. To do this, we can perform multiple dot products on the expression to get independent equations. We're not covering dot products in this video, but you can look it up online. So now we have the equation for the center of mass of the beam. But what if we care about another point, such as point Q? Here's the equation for the acceleration of point Q that we derived earlier. We can solve for theta using F equals ma, and then plug in theta to get acceleration of Q. Alternatively, we can also write the acceleration of Q in terms of the acceleration of other vectors. I'll skip the detailed derivation, but here's an expression for the acceleration of q in terms of the center of mass, given that both points are fixed on the same rigid body. Here, alpha is the angular acceleration vector, and the position vector is from the center of mass to the point q. To recap, today we have seen a general form of F equals ma in 3D. Dynamics is a big field, but next up, I would recommend learning the relationship between moments and angular momentum. The end goal of all this is to generate equations that describe the motion of objects on Earth. There are several approaches to doing this. You can use force and moment equations and convert them to scalar equations. Or you can use Lagrange's method, or Keynes' method, or D'Alembert's principle. Each of these is its own complicated yet fascinating topic. And that's it for this video. Again, if you want to learn more, I recommend checking out Professor Middigy's book on advanced dynamics.